I'm Li Junzhang from Nanjing University, China. I'm going to talk about fast rates for stochastic approximation of smooth and surrounding convex functions. This journal with Zhihua Zhou. So this is outline. Let's first see the review of stochastic optimization. So in this problem, we want to minimize the function capital F, which is defined as the expectation of a random function f sampled from distribution P. When both the domain capital W and the objective capital F are convex, this problem is referred to as stochastic convex optimization. A very well-known special case is risk minimization in machine learning. Here, XY is a random instance label pair sampled from some distribution D, and W is our model, and L is the loss function. And there are two approaches to solve this problem. The first one is the sample average approximation. So we basically sample n functions independently from the distribution P, and we minimize the sample average. The second one is the stochastic approximation. So it optimizes the problem directly by using noisy observations of the function. So a very famous method is SGD. I think everyone is familiar with SGD. The advantage of stochastic approximation is that it has a lightweight computation per iteration. So it could be very useful in practice. This paper we consider the stochastic approximation. And to measure the performance, we use X risk, which is defined as the difference between FWT and the minimal risk. Here, WT is the solution returned after T iterations. Next, let's briefly review the relative work. So for convex functions, we know that the risk is reduced on the order of 1/T. And when the function is both convex and smooth, we can improve the rate to 1/T plus square root of f psi over T. Here, f psi is the minimal risk. So it means that if f psi is very small, we can get the 1/T rate. For the surrounding convex functions, we also know that the optimal rate is 1/λT. Here, lambda is the modulus of strong convexity. So in both cases, we get a 1/T rate. Then we may ask, can we get rates that are faster than 1/T when we have both smoothness and strong convexity? In the literature, there do exist some faster rates for smooth and strong convex functions. However, they are limited to special cases such as least squares, an unconstrained problem, or the finite sum. And they may also require prior knowledge or very strong assumption. Next, let's see what are we getting in this paper. Okay, this is our assumptions. We assume that the random function is non-negative and L smooth. We assume that the expected function capital F is lambda surrounding convex. We also assume that the random function, the gradient, is bounded by some constant G. All of the assumptions are very standard. Because our algorithm is built upon the Apple gradient descent, so I briefly review this algorithm. This algorithm is actually very simple. It can be summarized in one sentence. It is SGD with restarting. So the inner loop is just the standard SGD. And in step 7, you use the average of this iteration, this epoch to initialize the next epoch. And in step 8, we double the epoch size and we halve the step size. The input of this algorithm is the initial step size eta1, the initial epoch size t1, and the total number iteration t, and the initial solution w0. Okay, let's see our algorithm, our fast algorithm for stochastic approximation. So it's also very simple. The input is first is L, the modulus of smoothness, lambda, the modulus of strong convexity, T, the total number iteration, and alpha is the parameter. In step 1, we just choose any point W bar in the domain, and we set the condition number kappa. And in step 2, we invoke epoch GD with half of T iterations and to get a good solution. So in this step, you can replace epoch GD with any other optimal algorithm for surrounding convex stochastic optimization. Because the goal is to get a solution W hat which have 1/λT rate. The case step is step 3. So in step 3, we invoke epoch GD again. But in this time, we use W hat as the initial solution. Given the fact that W hat is already a very good solution, so we use a larger epoch size, 2 to the power of alpha plus 3 and times kappa. So because it's already very good, so we utilize it more times to update for this long epoch. And the solution is denoted by W tilde. Okay, for this algorithm, we can show that it has the following theoretic guarantee. So when T is larger than kappa to the power of alpha, where alpha is some small constant that's larger than 1, we can show that in expectation, the X risk is on this order. We assume alpha is small, that's because we have an exponential dependency on alpha in our bound. So when it is small, the rate is 1 over lambda t to the power of alpha plus kappa epsilon over t. So it maintains 1 over lambda t rate in the worst case, but it could approach 1 over lambda t to the power of alpha rate when epsilon is small. So I give example when alpha is set to be 2. So in this case, we get 1 over lambda t squared plus kappa epsilon over t rate. And we may also want to check what happens when alpha is very large. So let's see, we choose alpha to be the largest value, which is log kappa t. So in this case, we introduce the constant c, which is 1 minus 2 times the log kappa 2. We can always increase the condition number kappa to make c very close to 1. Then you can show that our rate is on this order. So the first term will decrease at the rate of 1 over lambda and t to the power of c log kappa t. You see that this rate is faster than any polynomial rate because the log kappa t appears in the exponential term. Okay, this is comparison with the previous study. I think I don't have time to go through them, but the conclusion is that our setting is more general and our rates are faster. Okay, we also have a special algorithm for small risk. So this algorithm is even more simple. It just runs the epoch gradient descent, but use fixed step size and a fixed epoch size. For this simple algorithm, we can show that the X risk reduces exponentially until reaching the order of a star. So when epsilon is small, we get a linear rate, but if it is larger, we have a constant error. We can also have the iteration complexity. If t is on the order of beta times kappa and log 1 over epsilon, we get the X risk on the order of epsilon plus 2 times epsilon over beta. So it has a very nice dependency on epsilon. So in the case that epsilon is known, we can show that by setting t on this order, you get the epsilon of the solution. Okay. This is a comparison with the peer results. The conclusion is that our assumption is weaker and our rates are faster. Okay. The advantage of this paper is that all the techniques are very simple. We didn't use any advanced methods such as accelerated gradient descent, but get faster rates. And we only make use of a standard analysis of the GD and the self-bounding property of smooth and non-convex functions. And we also use the quadratic growth condition of the strong convex functions. The result is derived by a careful analysis and a new way of setting the parameters. Okay, let's conclude. So we propose a general algorithm which gets 1 over lambda t rate in the general and could be faster when epsilon is small. We also have a special algorithm for the small risk. The future work is to derive high probability bound and also extend our result to non-convex setting. Note that in non-convex settings such as neural networks, epsilon could be very small. So this kind of bound could be very helpful. Okay, thanks. But if you apply the standard concentration, you always have 1 over lambda t term. Yeah, you break the faster rates.
Okay, all right. So the next talk is on one of these freaky coincidences where 3 independent papers come up with the same result and then get merged here at the conference. So Pavel is going to give a talk on this amazing result, which has 14 different